let's look at two more examples of using the ratio test. Ratio test is really good when you have factorials and or exponentials in the expression for, oh, and I like k better, but then I forgot I was looking at a book example. And okay, when you've got factorials or exponentials in here, the ratio test works particularly well. So there's our a sub k. We want to know if this converges. Hopefully, well, since there's no minus signs, convergence is going to be equivalent to converging absolutely. These terms are all positive already, so that's not going to be an issue. So we're going to take our L, and we're going to look at the next term over the previous term. Absolute value, but as I said, that doesn't do anything. Okay, now we're going to have to do that real carefully. So we're substituting in a k plus 1 and tripling it and then factorialing it. And then 3k plus 1, and then the quantity k plus 1, factorial, and then cubed. Okay, and then times, well, we're dividing by this guy, so we're multiplying by the reciprocal. I'll go ahead and flip that, see if I can fit it in. 3k factorial. That's a little bit intimidating kind of expression, but I claim there's lots of cancellations, and we'll be able to figure out the limit of that as k goes to infinity. First of all, 3 to the k plus 1, that just cancels down to a 1 over 3. As we saw in the previous example, anything that was really a geometric series in disguise gives a constant factor. Now I need to be more careful about what happens with these factorials. Let me give myself some more room here. So it's got a 1/3 in front. So 3k plus 1 factorial, that should somehow hopefully cancel out with the 3k factorial. So let's see what happens with that. 3k plus 1 factorial, well, that's really 3k plus 3 when you distribute the 3, times 3k plus 2, times 3k plus 1, times 3k, times 3k minus 1, etc., all the way down to 3, 2, 1. Well, notice that's exactly 3k factorial times just this extra bit, but it's really important to get the extra bit correct. So this one, 3k plus 3, and then factorial, divided by 3k factorial is going to cancel down to just this. So any kind of thing with factorials is going to have a feature where you're only going to get a few terms left. But if you've got things like doubling and tripling inside, which is not super uncommon in applications of the series, you have to be really careful about exactly what cancels and what doesn't. Okay, so that has canceled these guys down to here. Then, well, k plus 1 factorial cubed, k factorial cubed, it's going to be the same thing as k factorial over k plus 1 factorial all cubed. Now this one is the simplest and most important factorial cancellation. K plus 1 factorial is just all the numbers in k factorial times just k plus 1. So all that cancels down to 1 over k plus 1. But it's all done 3 times. It's all cubed. So we're going to have a k plus 1 cubed on the bottom. Okay. This is exactly a limit of a rational function. And what have we got? We've got k, we've got a 3, k cubed on the top is the leading order, the degree of this polynomial, k cubed on the bottom. And I'm going to do it the quick and dirty way. I'm just going to say, well, what is the leading coefficient here? It's a 1 times k cubed plus blah, 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 blah. Here it's a 27 times k cubed plus other stuff. And the k cubes cancel, and you get 27. And don't forget the 1 over 3. And so we get 9. Now remember, what we're trying to figure out is it's a yes or no test. Is this below 1 or above 1? And if it is 1, we just discard the test and say it hasn't given us any information. This conclusively says that this is not convergent because this is way bigger than 1. These terms, even though they were sort of complicated to write down, it turns out that the 3k factorial on the top actually completely blows away the bottom. In a way that eventually it kind of looks like a divergent geometric series, roughly, with ratio 9. So this is divergent. Now I want to modify that example for the second one. I want to keep most of the keep all of it actually. I want to add something. This is really a step into the power series world. What if we had a whole family of series that I had some number x that I could choose, and the actual series of numbers was these coefficients times x to the k. So there's two ways to think about that. One is simply it's a bunch of different series depending on exactly what x is, or a bit of a different perspective we're going to take very soon is that it's a kind of an overgrown polynomial. It is a function of x that just happens to be defined by you have to sum a series to figure out what it is for any particular x. So here I just want to sort of take the first perspective. It's a bunch of different series, a family of examples all put together in a convenient way, and we could ask for which x, for which values of x does this converge? So this is a common way to take a yes or no statement, which we had before, the answer was simply no, and turn it into a more sophisticated thing. We know that if x equals 1, it's what the example we just had, and the answer was no. However, if x is very, very small, that might give a lot of help to convergence, because this, if x is like 0.01, this is going to get small real quick, and that might overwhelm the growth of this guy. And we actually even maybe have a guess. This guy was growing like a geometric series with growth factor 9. If I didn't have this, it would be a geometric series with growth factor x. Maybe that tells us what x might be in order to make it cancel out. So we'll be able to almost completely answer this question using the ratio test. So we just use the ratio test on the whole darn thing. And it's going to be very similar to what we had before. Oops, that's okay. Okay. And so, now the absolute value actually does do something, because x could be negative. And it's going to say something, it's going to produce an absolute value of x. So let me just write it down. And let's see if I can make sure I don't run out of room here. Okay, so I'm going to leave the absolute values in. That's the quantity 3 times the quantity k plus 1, all factorial, over 3 to the k plus 1, k plus 1 factorial cubed, times x to the k. Ooh, let me put that on the top here. Ooh, x to the k plus 1. That's what happens when you put in the k plus 1 term. Times the reciprocal of all the rest of it, the k version. That's going to be a little bit less room to write. Oh, and didn't do the reciprocal. That flips this stuff up. 3 to the k factorial cubed, 3k quantity factorial times x to the k. So once again, the 3's cancel down to just a 3 on the bottom, and the x's do the same thing, but now has an x on the top. And let's see if I can squeeze it in up here. Oh, I've got lots of room up here if I take out the title. Okay, let's take it up here. Okay, so everything here is positive except for the x. So I'm going to take out an absolute value of x. And of course, the 1 over 3 is constant. I can take that out. And then it's exactly the same limit we had before. Absolutely. That was, without the 3, it was a 27. Well, times the limit of all this stuff. So what we get is absolute value of x, 27 over 9, and you get absolute value of x over 9. Ooh, sorry, 9 absolute value of x, my bad. So the only thing different is that absolute value of x coming out. So this is a very common thing. When you have a power series, if you apply the ratio test in the usual way, you're going to get the same kind of thing you would have gotten from a numerical series of the coefficients, and then times an absolute value of x. Okay, we want this to be less than 1. Okay, so 9 absolute value of x less than 1, absolute value of x less than 1/9. You might have guessed that a few minutes ago when I was talking about how we want to counteract something that's basically looking like a geometric series with ratio 9. If I put in something else that has ratio 1/9 or less, that should help. So if this is true, then yes, the limit L will be less than or equal to 1, or less than 1, strictly less than 1, and it will converge. And it will converge absolutely. It's not trying to converge just because of alternating signs. Notice that when x is negative, this suddenly does become an alternating series. Okay, now if absolute value of x is greater than 1/9, then L is greater than 1 and diverges. If absolute value of x is equal to 1/9, then that's a little trickier because that takes us to the borderline case of the ratio test. For those cases, you're going to need to use something a little bit more sophisticated, and sometimes it can be quite tricky to see what happens in exactly those borderline cases. So I'm going to leave that for now. The ratio test has done a lot of good work, though. It's given us, for this whole family of series, no matter what x is, as long as it's not these two special values, plus or minus 1/9, it tells us conclusively what's going on.